Hello, Mr. Eric, Mr. Ryan, are you right? Okay, so we have talked about this graph problem for 2 days, right? So on the first day we talk about depth first search, on the second day we talk about the breadth first search. The problem is that we are given undirected, unweighted graph. Unweighted, undirected. Undirected basically means 2 ways, bidirectional. If a node A can go to node B, it also means that node B can go to node A. Okay, it's bidirectional. Okay.
That's not me. I could do it actually.
So the question is that we initially at node 0, and we are also given a list of nodes that we are forbidden to go there, and node 0 is not forbidden. Okay, so we want to find out how many nodes we can visit from the node 0. We can traverse the graph using the depth first search or breadth first search. Depth first search using the stack or recursion, breadth first search using the DQ, double NDQ, right? Double NDQ. So we also need to keep tracking of the nodes we have visited because we don't want to travel the same nodes twice, right? Just imagine if we don't use a hash set notebook to remember the nodes we have visited, we can go forward and backwards between 2 nodes endlessly. Okay, so because we are given a list of edges, right? So we need to build a graph, and in this case, it's better to use the adjacent list. Adjacent list basically is the key value pair. Okay, so we're given a list of edges bidirectional. So we need to use these edges to build a graph. There are 2 ways to build a graph. One is adjacent list. The other one is adjacent matrix. Okay. So the adjacent list basically is the key value pair, where the keys are the nodes and the value is the list of nodes that vertex is connected to. Okay. And adjacent matrix is a matrix. So basically, adjacent matrix 2-dimensional.
I didn't know that it is a matrix when it has the word matrix in it.
Yeah. Okay. So for example, adjacent matrix, right, is basically 2-dimensional, and each location we can note it as, for example, this is a matrix. Right? So Aij. If Aij is 1, then it means that there's an edge between vertex I to vertex j. And if it's for a weighted graph, we can use the value to represent the weight. Okay, so this part is just building the graph. This part is building the graph from the edges, and then we can perform the depth first search or breadth first search. This is depth first search, this is breadth first search. Today we're going to talk about solving this problem using the disjoint set union find. The reason we can apply disjoint set is because we want to find out, we just want to count how many nodes are in this group together with the node 0. Node 0, 1, 2, 3, 4, 5, 6, 7. Okay, like that. This is a unweighted graph. If I'm telling you that the node 2 and node 3 are forbidden, so how many nodes?
4.
How many nodes?
Do you count with 0? 6.
Yeah.
Then 4.
Using the depth first search, breadth first search, we can get the number 4. But today we're going to use the disjoint set. What's disjoint set?
Not known.
Disjoint set. Okay, so what can we do with the disjoint set? For example, given here, right? So look, there's an edge between 0 and 1. So 0 and 1, then we can say 0 and 1 belongs to the same group. There's an edge between 0 and 4. We can say that 4 is the same as this same group, right? Look, 4 and 7, there's an edge. So we can say, okay, these belong to the same group. And if it's in the forbidden set, then we just ignore, right? If it's in the forbidden set, we just ignore. If there's an edge here, we can say, okay, these 2 belong to the same group. So now, at the end, we just have to count how many nodes are in the same group as node 0. These 4 are in the same group, then we can easily get a number. Okay, this disjoint set is basically used for such application, okay? So with the disjoint set, we can perform the union find algorithm. What's union find? So it's basically 2. We can union 2 nodes, and we can find the node. What do you mean find the node? We can perform a find on a vertex on a node to find out which group it belongs to. So in this case, if we union 0 and 1, 0 and 4, 4 and 7, then we can find the parent, find the group of 0, 1, 4, 7. They all return the same ID. So then we can distinguish different groups. For example, 5 and 6 are in a separate group. Then we know it's different group and that, right? Get it? This is the data structure, and we can use it to solve this problem. And remember, we also talk about how do we find and how do we union two groups, how do we merge two groups. If, yeah, we talk about this scenario, right? If a group has like a million nodes, right? Now a million nodes are in here. This is a million node. And then there are only like 3 nodes in the group. We want to merge this group in here. Is it better to merge from A to B or from B to A?
B to A. You already asked this kind of question before.
Yes, why? Why we merge B to A?
Because there's like less nodes to put.
There are only 3, right? Though it's easier to move the 3 nodes to the bigger group because we just have to change these 3, right? Right? The cost is smaller. The cost is smaller. If we move this bigger group to left, then that's a lot of operations. That's a lot of cost. The time and space complexity for finding the parent and merging the two is amortized over 1 constant. Okay. Certainly, we want to maintain the disjoint set in such balance. Bless you. In such balance. What do I mean balance? Is that instead of like this kind of thing, right? This kind of thing, we want it to be something like that, right? Something like that. So the average cost of finding the parents is shorter. Look, it's similar to the binary search, right? If it's a linked list, it will be like degenerated. So what's the problem with this kind of diag structure? Because that it takes longer, because it's just like degenerated to a linear structure. So it takes time to travel from one end to the other end. And on this side, we want to maintain such a balanced structure, so it takes less average time to find a parent in a disjoint set. Okay. Yeah. And then when we merge the 2 structures, we want to be making the smaller group belongs to the bigger group. It costs less to do so. Yeah. So let's just write the code. It could be quite simple, right? It's quite simple to use the disjoint set. Let's say disjoint set equals disjoint set with the n vertex. Then we go through the edges for A, B in edges. If A in restricted set or B in restricted, right? If this edge contains the vertex which is in the forbidden, then we just ignore it. We can continue. Continue. C-O-N-T-I-N-U-E. Continue. Otherwise, we just said disjoint set dot union or merge union. Okay. Union A and B. So what does it mean? It means that let's merge the group of A to group of B. Okay. So A and B belongs to the same group. Okay. And at the end, that's it. At the end, we just return disjoint set dot count the 0, right? So this function basically going through the nodes and find out which node has the same group as the node 0, and that's it. Look, that's it. The time complexity. Look, we're going through the edges. This is O-E actually. Okay, O-E, and then we merge it. This is amortized over 1 constant, and then we count it. Okay. So I'm not going to implement this. Yeah, we have talked about how to implement the disjoint set, right? Just using the array, we can easily using the array to implement the disjoint set. There are only 2 functions we need to implement for this. One is the union, the other one is to find. So the pseudocode will be something like that. Okay, if you want to merge, if you want to union to merge A and B to the same group, we need to check if the parent A, if the A and B belongs to the same group. If it belongs to the same group, then we don't need to do anything, right? If it's different group, then we need to find out. We need to find out how many nodes for the vertex A and how many nodes for the vertex B. And we want to move the smaller group. We want to attach the smaller group into the bigger one instead of the bigger group to the smaller one, right? And then we update the count for each group. Okay? And then the count function, ds.count function, just basically going through all the groups, all the vertex, and check if their group ID at the beginning, if there are n vertex at the beginning, right? N vertex at the beginning, we can just say 0, 1, 2, 3. This is the initial state for the n vertex, right? And then we just have to go through this, iterate this internal structure to find out which number, which vertex has the same group ID as the vertex 0. Okay, so look, this pseudocode is quite simple, right? And in this case, actually, in this method, we don't actually need to build a graph, right? We're not building the graph, we just go into the edges and then find out to merge two edges, two vertex if neither of them is in a restricted set. Okay, so look at this continue keyword, right? When it's running in the continue, it means that it does not execute the remaining statement in the for loop. You just continue, right? Alternatively, we can inverse this. So if not A in R and not B in R, then we do this. Okay, this is the same thing. Okay, so what have you learned today?
We have this like
So how do we solve this problem?
kind of like link.
Hmm?
These kind of like link to nodes, and if there's in the same like, if they like somewhat like linked to node 0, then the amount of nodes which are somewhat linked to 0 is the answer.
Yeah, okay, good. So basically we want to find out how many nodes in the same group as node 0. And how do we find out the group? We just when we have an edge from A to B and neither A or B is in the restricted
That thing turned
graph.
up.
Okay? Neither A and B is in the restricted set, and we merge the group of A to B, right? And then at the end we just check how many nodes are in the same group as node 0. Simple as that. The idea is quite simple, right? The idea is quite simple. Actually, this disjoint set is quite beautiful data structure. Okay, it can be used to solve this problem in a more elegant way. Okay, so there are 3 ways to solve this problem. Okay, depth search, breadth search, and disjoint set. Okay, that's it for today. Bye bye. Bye.